Hi everyone, welcome to our last lesson in chapter 8. This is 8.3. We're looking at the number of solutions. The number of solutions refers to how many solutions a system can have. In other words, how many points of intersection can one system have. We're looking at systems of linear equations. So in other words, one graph where two lines have been graphed on that same graph. And there are only a couple of possible scenarios that we can have. So, for example, up to now, we might have looked at a graph like this, okay, where we graph two lines on the same graph and they cross. So they're not parallel lines, which means that they will cross somewhere. And there's only one point of intersection. It's this point right here. Okay, there is one point of intersection. The solution is the point where they cross, which is 1 for x. If I come down to the x-axis, that's at x equals 1. And if I come over to the y-axis, it's at y equals 1. So that solution is 1, 1. There is only one point of intersection. And so we say that there is only one solution. In other words, there's one point of intersection and it is 1, 1. But it has only one solution because they only cross in one place. Okay. Well, you might ask yourself, well, what other possibilities could I have? Well, there are three. Okay, so here are the three types of systems that we could encounter. In other words, the three possible scenarios. The first one is that our lines, the two lines that we graph, are intersecting lines. Okay, so they cross. They have different slopes. And anytime you have different slopes, eventually they will cross somewhere. So if I had a look at this, these two lines could be perpendicular, or they could just be any two lines with different slopes and they cross somewhere. So there's only one point of intersection, so there's only one solution. Okay, only one solution. So lines that cross are called intersecting lines, and they will have one solution because they only cross in one place. Let's write that down. They cross in only one place or point. Okay. The other option that we've seen already is when you have parallel lines. Parallel lines never cross. Okay, they have the same slope, which means that they will never cross. They are railroad tracks, they'll just always run in the same direction in the same plane. So they have zero solutions. Okay, in other words, there is nowhere that they will cross. Okay, so we say no solutions. The other option that we could have is that we have two lines, but they have the exact same equation. So this would be, as a word problem, you have two situations where the rate of change is the same and they both have the same initial value for y. So we get the same equation for the line. So if the lines have the same equations, which means same slope, okay, same b value, same y-intercept, they will actually, when you graph them, they will lie right on top of each other. We call these coincident lines. I always sort of remember that it's a coincidence that they have the exact same equation. So these are overlapping lines. You don't have to graph them to figure out that they're overlapping. If you are given two equations and they're the exact same, you know that those two lines, when graphed, would be right on top of each other. They would be coincident lines. And that means that everywhere on the line is a shared point with the other line. So we say that they have an infinite number of points. Infinite means unlimited, essentially. So another way of thinking of that is they cross everywhere. Okay, because they're overlapping, they cross at all points on the line. And so what we say there is that they have an infinite number of solutions. So there's no limit to how many solutions they can have. Okay? So the trick here when you're looking at coincident lines is sometimes you might be given an equation of a line like this, y equals 3x plus 6, but you're given another equation that maybe isn't in slope-intercept form. So here we have 2y equals 6x plus 12. I would want to divide that second equation through by 2 so that I have y equals, if I divide this by 2 and I divide everybody by 2 here, I get y equals 3x plus 6, which I see now actually is the same equation as the first line. So let's go ahead and look at some of those. So how to recognize these lines? This is important. Okay, so if you're looking at a graph, intersecting lines are really easy to recognize because they have different slopes, okay, and you can see clearly that there's one point of intersection. Okay, that's how I would see that on a graph. If I was looking at an equation, y equals mx plus b, I would have two lines, so I'd have two equations, and I would see that the two equations are different. Okay, so two different equations, and by that I mean different slopes. That's the key. Okay, so m is different. Okay, they have different slopes. They could be perpendicular lines so that their slopes are negative reciprocals, or they could just be different slopes. Okay, so I'm looking for different m values. For example, y equals negative 2x plus 8. Okay, m is equal to negative 2. There's my slope. The second line is written in y equals mx plus b form, which is good. And I'm looking at the slope, and here I see that the slope is equal to 1. They have different slopes, so they will eventually cross somewhere. Okay, they're intersecting lines. The number of solutions will be 1. One solution, 1 point of intersection. Parallel lines, again, we've looked at these before. On a graph, we could recognize them because they look like railroad tracks. Railway tracks. They run in the same direction. You can see just by looking at them that they're never going to cross. Okay, if you're looking at their equation written in slope-intercept form, y equals mx plus b, they will have the same slope. So m1 will be equal to m2. They will have the exact same slope. For example, if I'm looking below here, y is equal to negative 2x plus 8. There's line 1. The slope, m, equals negative 2, or negative 2 over 1. The second line, y equals negative 2x minus 1, the slope is also equal to negative 2. So we have the same slope, which tells me that they're running in the same direction, but b is different. Okay, so here b equals positive 8, and here b equals negative 1. So they have to have the same slope, but different b values, different y-intercepts. They have to have different y-intercepts because if the y-intercept was the same, they wouldn't just be parallel, they would be the same line, or in other words, they'd be coincident lines. So same slope, different intercepts tells me they're parallel, and there are no solutions for parallel lines because there's nowhere that they cross. Okay, finally the last type of example I could have are coincident lines. So if you have two lines on a graph and they're right on top of each other, I'm looking and seeing that they're overlapping. That tells me I can recognize coincidence lines by a graph because they'll be overlapping. If I'm not given the graph, I'm just given an equation. What am I looking for? I'm looking for the exact same equation. So I'm looking for my two equations to have the same slope and the same y-intercept, so the same b value. So for example, y equals negative 2x plus 8. There's my slope. M equals negative 2. B equals 8. The second equation that I'm given here says 2y equals negative 4x plus 16. If one of your equations is either out of order or we don't have a single positive 1y on the left-hand side, we have to rearrange it and divide through in order to get 1y equals mx plus b. So remember, you need to be in y equals mx plus b slope-intercept form to compare two equations. So here to get that into y equals mx plus b, I have to divide the y by 2. And if I do that to the y, I have to do that to everybody. So let's go ahead and now simplify that. So my answer is going to be 2 divided by 2 just gives me y. Y equals negative 4 over 2 reduces to negative 2 over 1, or negative 2x, plus 16 divided by 2 is 8. So now I can compare it to the equation above it, which represents another line, and I see that m is right here. M equals negative 2. B is equal to positive 8. So they have the same slope and they have the same B value, the same y-intercept. So they are coincident lines and they have infinite number of solutions. So they overlap everywhere, so there is no limit. Okay. Let's just really quickly finally look at a couple of more examples and then I'll give you a chance to try some yourself. So let's, it says predict and verify the number of solutions for the linear systems. I'm going to do one or two of these now and then I'll just finish the last two in another really short video. So let's start with number 1 here. It says we have y equals x plus 4 and y equals x plus 7. Two different lines. Let's see what kind of situation we have. Are these parallel? Are these perpendicular? Are these coincident lines? So the first thing I look at is I see that they have different equations. Okay, so I know they're not coincident lines. But if I look at the slope, m is equal to 1. In the second equation, m is also equal to 1. Okay, but b is different. So these lines have the same slope. They are parallel lines. Which tells me that there is no solution. Let's go ahead and do the next one. So we've got y equals 2x plus 8 and another line, y equals negative 4x minus 9. The slope here is 2 for the first line. In the second line, the slope is negative 4. So right away, I don't have to go any further. I can see that these have different slopes, different equations. Remember, different slopes will cross somewhere. So these are intersecting lines because eventually they will cross. Okay, so they have one solution. I'm going to just go up to the example 1 for a minute. Just take out the word verify. Let's just say justify. Rather, sorry, verify was the wrong word here. So we're justifying that there's one solution by saying that they're intersecting lines. They'll eventually cross. I'm going to stop there and I'm going to continue the last two examples in a really short video after this.